Hello everyone, so today I'm going to present to you about Principal Component Analysis or PCA. So what is PCA? Principal Component Analysis is a dimensionality reduction technique that simplifies complex datasets while retaining essential information. PCA transforms a high-dimensional dataset into a smaller one by creating new attributes called principal components. The principal components are uncorrelated variables that representing directions of maximum variability in the dataset. And each principal component captures a different aspect of variability, allowing for efficient reduction of dataset dimensionality. So how does PCA work? So actually PCA have 5 main steps. First is standardize the data. The second one is compute the covariance metric. The third one is compute eigenvectors and eigenvalues. Fourth one is select principal components and create a feature vector. And lastly, transform data. So let's see one by one. First, to standardize the data. PCA requires the dataset to be on the same scale, which means that it is crucial to standardize the dataset before applying the PCA. Second, compute the covariance metric. The covariance metric of the standardized dataset is being calculated for further steps. Third one, compute eigenvectors and eigenvalues. Both eigenvectors and eigenvalues are computed to identify the principal components. The eigenvectors are sorted by their respective eigenvalues in descending order. This will give us the principal components that are sorted in order of significance. Fourth, select principal components and create a feature vector. The principal components or the top eigenvectors are picked based on the selected number of dimensions. The selected principal components are used for creating the feature vector, which is the metric that has the columns of the principal component we keep. And lastly, transform the data. After we get the standardized data and the feature vector, they are both multiplied up to which result in a reduced dimension data set. Next, let's talk about how we can tune the parameter for PCA. PCA usually have one main parameter, which is the number of principal components to preserve, which impact the dataset dimensionality and information retention. Tools like RapidMiner offer options to set the number of principal components either with a fixed number or by specifying a variance threshold. Tuning the number of principal components involves finding a balance between simplicity and information preservation, achieved through experimentation and performance evaluation. So next, let's talk about the applications of PCA in some fields. First, let's talk about the biology and medical. A variant of PCA is used in the neuroscience field for identifying the specific property of stimulus that affect the probability of a neuron generating an action potential. Let's see about financial field. In analyzing correlations among numerous stocks in a portfolio, PCA can significantly decrease dimensionality from 100 by 100 metrics to a smaller dataset while preserving variance, streamlining analysis, and interpretation. Next, for the software field, we have the use of an array of eigenvectors called eigenfaces. Applying to facial recognition is created by using PCA, as it helps generate the collection of possible faces that may occur. It improves the simplicity of face image depiction while also maintaining the essential characteristics. And the last one is image completion. It also uses the PCA. PCA significantly lowers the dimension of an image while precisely retaining its quality and appearance of the image. Next, let's talk about my dataset. My dataset is called Allied Passenger Satisfaction. It contains survey results measuring passenger satisfaction within an airline. With 25 attributes initially, the dataset includes non-essential attributes like roll number and ID of the passengers, totaling in 23 attributes that are suitable for analysis. The dataset contains passenger details, travel information, satisfaction, rating, and delay times, collectively contributing to the assessment of an airline passenger satisfaction. Here is the dataset before pre-processes with PCA. So the dataset undergoes pre-processing steps, such as handling missing value, converting satisfaction to a binary label, transforming nominal attributes into numerical by using dummy encoding, and standardizing all attribute with such transformation. The result in a dataset containing one label attribute, which is the satisfaction, and 27 regular attributes, which elevating its complexity. So the dataset after pre-processes with PCA, I apply a PCA with a variance threshold of 0.9 to the dataset, which replaces the regular attributes with principal components. This reduces the dataset's dimensions from 27 to 15 attributes, nearly halving its size. These simplifications enhances model training efficiency and data processing speed, contributing to improved overall simplicity and performance of model training. Next, I will talking about evaluation of PCA technique. So I divided the evaluation into three parts, which is predicting the passenger satisfaction without using PCA. Second is to predicting the passenger satisfaction with PCA applied. And the last one is to predicting the passenger satisfaction with LDA, which is the other technique. First, predicting the passenger satisfaction without using PCA. The accuracy I got is 92.74% with the execution time of 163 seconds. So after pre-processing, I apply the k-nearest neighbors or KNN algorithm, which achieves a high accuracy of 92.74% in predicting passenger satisfaction. However, due to increased dimensions, the execution time for applying the KNN to the dataset rises to 163 seconds. Next is when I'm predicting the passenger satisfaction with PCA. So the accuracy I got is 91.7% and execution time of 90 seconds. So after applying PCA with a variance threshold of 0.9, it slightly reduced the KNN accuracy to 91.7% from 92.74%, which is about 1% from when without using the PCA. However, it significantly cuts down the execution time from 163 to 90 seconds. While there's a slight loss in accuracy, PCA reduces computation complexity and enhances algorithm efficiency by trimming the dimensions. Next one is by comparing with the other technique called LDA. So I got the accuracy of 87.05%. So after employing linear discriminant analysis or LDA for dimensional reduction and classification, the accuracy decreases to 87.05%. LDA does not effectively reduce dimensions and use lower classification accuracy compared to KNN with and without PCA. So in summary, PCA proved more suitable for dimensional reduction with better accuracy for this dataset than the LDA technique. Next, let's see about the demonstration. In this demo, I will use RapidMiner to show you how we can apply PCA into the dataset to reduce the dimensions of the complex dataset. First, let me show you how I pre-process the data before applying PCA. So first of all, I remove the data with missing values Then I exclude the attribute that I don't use, which is the roll number and the ID of the passenger. Next, I transform the satisfaction from nominal to binomial and then set it to the label. And lastly, I convert the other nominal attributes into numerical with dummy encoding. After that, as PCA requires normalization or standardization, so I normalize it with set transformation. So let's see. So here is the dataset before applying PCA. As you can see that it has 27 regular attributes with one special attribute, which is the satisfaction, which is the label. And here is the dataset after applying PCA. You can see that it has only 15 regular attributes, which is the numbers of principal components we preserve using 0.9 variance threshold. As you can see that it simplifies the dataset to almost into half. So next I will show you how I classify the satisfaction of the passenger by using KNN with the K value of 7, which is the optimized value. And I'll skip to the result. So this is the result of applying KNN classification to classify the satisfaction without using PCA. So as you can see that we have 27 attributes here, and here is the result of the satisfaction. And when we look at the performance, we have the accuracy of 92.74%, and it took 2 minutes and 40 seconds. So next I'll use PCA. So this is the steps, the same steps, but I'll add PCA to reduce the dimensionality of the dataset before applying KNN classification. So let's run it. And I'll skip to the result. So here is the result of satisfaction classification with PCA applied. So you can see that it has only 15 principal components. And this is the result accuracy. So we have 91.7% in accuracy, which is just decreased by 1%. But you can see that the time is reduced from 2 minutes and 40 seconds to 1 minute and 52 seconds in this demo. Last one, I will show you the LDA. So this one, I will not use PCA, but I will later use LDA to dimensionality reduction and performance classifications. So here, as you can see that it can also predict the satisfaction of the passengers and will run faster. The accuracy is just 87.05%, which is decreased by much compared to KNN algorithm with and even without PCA. And that is for the demo. Next, let's talk about the advantages of PCA. So first one is dimensionality reduction. PCA reduces the number of dimensions. It simplifies the dataset while retaining the information. Second, multicollinearity handling. PCA removes multicollinearity. This happens because the principal components from PCA are orthogonal to each other, which means that they are uncorrelated. Third one is visualization. So by reducing the number of dimensions, it is easier to visualize the lower dimensional data. Fourth, model training time reduction. So with the lower dimensions, model trainings can be done faster as the data is more simplified. Fifth, noise reduction. PCA can help reduce the impact of noises in a dataset by projecting the data in a lower dimensional space. And last one, feature selection. PCA can help us analyze the importances of attributes by using the principal components acquired to identify the important features. Next, let's talk about the disadvantages of PCA. So, first one is the loss of interpretability. The principal components cannot be interpreted the same way as normal attributes. Second, information loss. So by reducing the dimensions, it can help simplify the dataset, but come with the expense of loss in information. Third, assumption of linearity. PCA assumes that the dataset is linear, even though the dataset is not actually linear. Fourth, sensitivity to outlier. PCA can be distorted by outliers, which can affect the accuracy of the results. Fifth, computationally intensive. So applying PCA on a large dataset requires intensive computation. Last one, requires scaling. PCA is a technique that requires data to be on the same scale before applying. Next, I will talk about comparing PCA with the other technique in the same category, which is dimensionality reduction. So first, let's talk about comparing PCA with linear discriminant analysis, or LDA. First, PCA is unsupervised learning, while LDA is supervised technique. Both are linear transformation technique that performs data metric factorization. PCA reduces noise, removes multicollinearity, and captures most important dimensions. It is applicable to various data types. LDA improves classification performance and accuracy by enhancing class separation and preserve information. PCA may cause loss of information due to dimensionality reduction. LDA aims to preserve information related to class separation, minimizing information loss. PCA can lead to loss of information, especially if important features are spread across multiple dimensions. LDA prone to overfitting if class distribution is imbalanced, as it may prioritize separating classes that are not representative of the overall dataset. Next, I'll compare PCA with the independent component analysis, or ICA. So PCA optimizes the covariance matrix of the data representing second-order statistics, while ICA optimizes higher-order statistics such as kurtosis. PCA finds uncorrelated components, which is the principal components, while ICA finds independent components. PCA extracts independent sources when higher-order correlations of mixture data are small or insignificant, while ICA extracts independent sources that are independent of higher-order correlations. PCA focuses on the major components' mutual orthogonality. ICA does not emphasize the components' reciprocal orthogonality. And PCA decreases dimensions to avoid the overfitting issue, while ICA decomposes the mixed signal into signals of its separate sources. Last one, I'll compare PCA with the T-distributed stochastic neighbor embedding, or TSNE. First, PCA is a linear dimensionality reduction, while TSNE is a nonlinear dimensionality reduction. PCA does not perform well as compared to TSNE. TSNE is considered one of the best techniques. PCA does not have any hyperparameters, while TSNE involves perplexity, learning rate, and number of steps. PCA highly affected by outlier, while TSNE can better handle outliers. PCA take less computationally expensive, while TSNE can be computationally expensive, especially for high-dimensional datasets. PCA used for visualization, but it's less effective compared to the TSNE because TSNE specifically designed for visualization and perform better. PCA is suitable for linearity separable dataset, while TSNE more suitable for non-linearly separable datasets. And here are my references. And thank you for watching.